Welcome to another restoration. Today we're talking about the Worldwide Electronics Magnadyne Premier Model P659. It's a portable diathermy machine, brought to you by Consolidated Rubber Fasteners. We received the diathermy machine at the Sacramento Valley Medical Society's Museum of Medical History. We don't have any good information about the unit as we received it. It was said to have been in service performing diathermy therapy for many decades. The technology of the unit is 1950s or earlier vacuum tube technology. Beyond that, we don't know very much about it. We don't have a manual. We don't have a schematic. So we're going to have to figure it all out. So what is diathermy? What's a diathermy machine for? Diathermy is a type of medical therapy which provides deep tissue heating to improve circulation or promote healing. It was also suggested as providing benefits of an artificial fever to fight infections or kill cancer cells. I don't know, I'm unaware of any information that suggests that it's effective for those kinds of therapies or does anything that way. But certainly things like deep tissue heating is therapeutic for certain conditions. So, you could do this. It's kind of, if you've ever wondered what sticking your hand in a microwave oven would feel like, that's what this is. That's what this is supposed to provide. And so a diathermy machine makes radio frequency electromagnetic waves, and you put a couple of pads around a body part, and it microwaves you. This is the unit, the way the museum received it. You can see it's kind of a cabinet-based thing. It's got a carrying handle on top. It's heavy as all hell. And it has a front panel that's very, very simple. It has a little on-off knob associated with the timer, so you can turn the knob, start the timer, and put the pads around the patient for some specified amount of time. The power control knob on the front of it is designed so that when you turn the power control knob, you're tuning the oscillation frequency of the circuit in order to bring the patient circuit into resonance with the driving circuit inside the cabinet, and then that allows the driving circuit to apply microwave or shortwave radio wave radiation to the patient, and the patient is supposed to feel a sense of warmth or heat. You have to be careful in applying this kind of stuff. You can cause burns or tissue damage if you don't know what you're doing, and I certainly don't know what I'm doing with this, but we'll get to that in a minute. It's got a meter on the panel that the dial will show how much current the circuit is drawing, which is sort of a loose indication of how much energy or heat you're applying to the patient. When we plugged a thing in the museum, all it would do was the light would go on briefly, and then it would pop the fuse on the back of the unit, and if we managed to get around that, it would just blow the circuit in the building, so we didn't do that. Okay, so opening up the back of the cabinet to see why it kept popping its circuit breaker, one of the obvious things to see here is that the wiring is in pretty bad condition. There's a lot of rust formed on the inside of the mounting plate where the circuit is located, and so the first thing to do would be take it apart and fix the obvious shorts that you find, and then see if that doesn't improve things. So after repairing the obvious stuff that was wrong, and then having a look further on the inside, it was clear why we were blowing fuses, because the unit was, as we say, the victim of prior repair attempts. Somebody had wired the AC power input to a dead short, so as soon as you turned it on, it would just short itself out and pop the fuse. So straightening that out caused it to stay on longer, but the vacuum tubes would immediately just go to rail fully saturated, and nothing was resonating with anything, and you couldn't change the behavior at all by tuning it. So now we just have to understand what the circuit is trying to do, and then see if we can't make it do that again. So we replaced the timer, which was shot and was badly pitted, as I say, on the inside from decades worth of service. And so the easiest thing to do rather than try to repair this thing on the inside was just see if we could find another one. And sure enough, somebody was selling lots of these things on eBay for 15 bucks. We'll get you three. And those three needed a little disassembly and lubrication on the timer. It's really just a clock timer, and then away we go. We got new ones. So now we had to try to understand what it was designed to do. The circuit is made out of two vacuum tubes with their outputs coupled together in a push-pull configuration. We'll talk about that. And the push-pull configuration was driving a resonant LC or inductor capacitor circuit. The inductor coil, the idea here is the inductor coil that couples together the two vacuum tubes drives an unconnected smaller coil by inductance and a capacitor in series with the patient pads. Okay, so the patient pads are capacitors which participate in this second resonant LC circuit. When the patient pads surround a body part, that changes the capacitance of the circuit, and then by turning the knob on the front of the panel, you're changing the total capacitance of this second LC circuit, and by tuning that circuit, you bring it into resonance with the natural frequency that the rest of the vacuum tube circuit is constructed to have, and so then that will allow power to flow inductively coupled from the vacuum tube circuit into the capacitive pads around the patient, and that deposits radio wave energy into the patient, and the patient will feel that as heat or warmth, and hopefully not too much. Okay, so here we see the inside of the circuit that needs repair and understanding. And so on the top there you can see two kind of square-shaped metal plates. That's the capacitor in the main vacuum tube circuit. And then to the right of that is a tunable variable capacitor, which is in the patient circuit. And below that you can see a large coil that's mounted on a couple of ceramic standoffs. That's the main inductor coil on the vacuum tube circuit. And the thing that bugged me is if the vacuum tube circuit is supposed to oscillate, you have to have some feedback from the output of the vacuum tubes back to the grids, which control the vacuum tube circuit. The grid on a vacuum tube is really, if you don't know what a vacuum tube is and how that works, a vacuum tube is it's like a transistor, but a really bad one, which is funny because back in the day, transistors were said to be like vacuum tubes, but not as good. And now transistors are much better. And so the grid on a vacuum tube is really the same as the base on a transistor, or in the modern field effect transistor era, it's really the same as the gate pin on a FET, for all of you younger people who don't know about vacuum tubes. So there's no connection from the output of the tube back to the grid, so that you're never going to get it to oscillate this way. It's just going to sit there and run to rail. So what I really needed was somebody to kind of provide me with a diagram of how this circuit was supposed to function in a working unit. And so you got to hit the interwebs and see if anybody has written anything about this. And I found a bunch of old patents for diathermy machines that worked basically this way. It was a very informative Army technical manual from 1944 for wartime use of diathermy machines for patients presumably that needed some kind of treatment in the war. And then after that, I ran into the really key thing. The really key thing was a book called The Radio Handbook, the 7th edition, published in 1940, which was supposed to be a compilation of columns and informative stuff for amateur radio builders or people working with amateur electronics. And it had a whole chapter on radiotherapy, i.e. diathermy. Now the chapter is only 5 pages long, but the circuit that they provided to make your own diathermy machine was nearly exactly what we have here in the Worldwide Electronics Magnadyne Premier P659 unit that we have. So studying that circuit really allowed me to figure out how this was supposed to work, what it's supposed to do, and gave indication of how we're going to fix this. So what our circuit had was basically everything shown there in the circuit. I mean, they're doing a little fuzzy business about the way the step up and step down transformer part of the circuit are shown, and that's nothing more than just a transformer that takes the 120 volt AC power and gives you the high voltage that you need to drive the vacuum tubes, and also the low voltage that you need to run the filaments on the vacuum tubes. And so the left half of the circuit diagram is nothing more than just sort of the power input section. And up at the top, you can see the two vacuum tubes up there, and they're coupled together with lines that go from the output back to the grid pins, and the coupling happens through two capacitors labeled C2 and C3 there, which we simply didn't have in our unit, and I don't know why they're not there. I don't know if our unit was supposed to have functioned by just the like stray capacitive pickup or stray inductive pickup to the output, but it was never going to work that way. So I added a couple of the capacitors with the values suggested in this circuit here, and that seems to work. Here we've got the underside of the circuit where you can see the two tube base mounts and a couple of the inductors. So let's fire this up and see what it does. Here's the Diathermy machine demo, and we're going to also show you what it does to FM radio transmission. So you power it up with the timer switch. We're on.
He's sending a delegation to Washington to weigh in on those nuclear talks with Iran. Israel is not a part of that U.S.-Iran deal, and it remains concerned. But again,
I think it's something in the neighborhood of could be 40 to 75 or 80 megahertz, a little unclear. And then so I've got this dummy load set up here. This is a mock-up for a person. So I have a couple of containers of just electrolyte solution, and I have the two capacitive paddles surrounding the tissue. So we switch on, and you can see the current draw is 70 or 80 milliamps, and then as you tune the capacitor to come into resonance, the capacitor runs on this circuit here. The patient paddle circuit doesn't connect up to the rest of the power generation of the RF. It's inductively coupled with a coil that I'll show you in a minute. And so when you tune the capacitor that is in series with the patient paddles, you can see the current draw as you approach resonance gets bigger, right? And so now we're really applying heating to the patient. You have to be a little careful. I'm not sure I have the circuit completely right at this point, but anyway, you don't want to let the current go above 300 milliamps, they say. So okay, we're approximately in resonance now, and you can see as I move my hand near the paddles or change the position of the paddles that the resonance changes, right? You watch the needle flick as I put more tissue inside the thing. Let's have a look at the back end of the thing. It's kind of a beast. You can see the two amplifier tubes, and then the big tunable capacitor and the static capacitors that tune the tubes into resonance, and then the variable capacitor then changes the patient circuit, and all this wonderful inductive coupling and stuff. And frankly, the tubes get hotter than I think that our tissue heating would. Anyway, so let's just detune the thing and then switch off, and you watch the meter go down as we detune. Switch off. So the tubes themselves, these CV11 vacuum tubes, are supposed to source something like 65 watts each maximum, and so you have the two of them going together, and you probably shouldn't exceed, I think, 320 milliamps on the panel meter, and we'll try to make sure we don't do that. Then there's one more capacitor value to kind of tweak. And then we'll just leave you with a couple of shots of the glorious glowing tubes on the inside, and then one final shot of the the wonderfully restored plastic panel, which has been polished to a high sheen. Anyway, so, okay, it works again. I haven't yet been brave enough to stick a body part in here. No, that's not true. I did actually stick my elbow in there, and you can feel it. It does. It gives you a gentle sensation of deep warmth, and we're going to mess with that a little bit more and see what else you can do with this. So, thanks for watching, and please visit the Sacramento Valley Medical History Museum to see this and other interesting artifacts.